Hi everybody, today's kind of a big day. I get to show you some things about similar triangles. There are three different ways to know that triangles are similar. The primary one, the one that we'll use most often, is angle-angle. And this purports that you probably know a little bit about that already. And here we talk about a couple of triangles that in fact are similar, probably by angle-angle. Tells me that AB is perpendicular to BD, so we expect a right angle here, and also that BD is perpendicular to DE. So yeah, we got a couple of congruent angles already, don't we? The right angles are congruent with one another. And you're probably recognizing that the vertical angles are congruent as well. Should mark them that way, then it becomes obvious. So I got two angles in this triangle congruent to two angles in that one. Truth is, that makes the third pair of angles congruent. And then for all three angles in this smaller triangle, ABC, are congruent with all three angles in the bigger triangle. So it asks me right away, why would the triangles be similar? And I'm going to make a couple of notes with you. I would say the vertical angles congruent, because we certainly did consider that. Vertical angles are congruent. And how about those right angles too? Right angles are congruent. And those two things go together to make me think we have congruent triangles. It's not congruent, but similar triangles. So triangle, I'll call this first one ABC, is similar to triangle. I think angle A matched with angle E. Let me get so you could get a look at that. So this is going to go with E, and the right angle at B, the right angle at D, EDC by angle-angle. That's why I think that these triangles are similar. And it tells me some lengths. AB is 6. Put it on that sketch. BC is 8. Well, DE is 15. Find the length of CD. And I got to think to myself, does this CD correspond to a side in this triangle? And because it's opposite this angle at E, which we knew was congruent to this angle at A, opposite angle at A, this side of length 8, opposite the angle at E, would be CD. So those are going to be corresponding sides. I'm thinking that 8 is to CD as, then what's the ratio between these couple of triangles? And again, opposite the congruent angles, these vertical angles are congruent, opposite the vertical angle here gives us the length 6, and opposite the congruent angle there gives us the length 15. They're in a ratio of 6 to 15, these two triangles are. I could have reduced that 6 to 15, probably would have been a good idea. The triangles are in a ratio of 3 goes into both of them, 2 to 5. We'll use that thought in a minute. These triangles are similar in a ratio of 2 to 5. When we cross multiply and solve this thing, 8 times 15 is 120 equals 6 times CD. And I want to know the length of CD, so I'm going to divide both sides by 6. You probably agree with me now that CD has length 120 divided by 6 ought to be 20. Hold that thought. Let me consider if that works. CD ought to be 20. Things are in the ratio of 2 to 5. Does that work that okay? 2 is to 5 as 8 is to 20. Yeah, I think I'm getting 40 either way I go there, so I'm happy with that. This thing should have been 20. Here's a pretty good question now. What's this? AE, and AE goes all the way from here to here, is 35. What about these two parts? Well, the hypotenuse of this right triangle is going to correspond to the hypotenuse of that right triangle. So these two parts must be in that ratio of 2 to 5. And what else do we know about them? These things are in the ratio of 2 to 5, but they got to add up to 35, don't they? And a really nice way to work through that would be, call this one 2x. I don't know what x is yet. And call the other one 5x. I know they're in a ratio of 2 to 5. I can call them 2x and 5x. And say that they add up to 35. Solve that little wimpy equation. We got 7x equals 35. So now I'm convinced that x would have been 5 when I divide both sides by 7. So one of those segments must have been 2 times 5, and that would have been 10. I'm thinking that AC is equal to 10. And the other one was 5 times 5. That would have been CE. CE is 25. And that works out pretty well. They do add up to 35, don't they? Which is important because AE had to be 35. But also, they're in a ratio of 2 to 5. So, done with that question. Let's look at this next one. We're still talking about triangles being similar by angle. And this tells me about a couple of angles in a triangle PQR. Angle P is 60 and angle Q is 80. Well, angle in the second triangle, XYZ, angle X is 40 and angle Y is 80. I think I'll make a sketch. Take a look here. I made a triangle where angle P was 60 and angle Q was 80. That's a P right there. And a triangle XYZ with angle X being 40 and angle Y being 80. And I wonder, are those triangles similar? And those angles aren't congruent. But if we think a little bit more about this, since these two angles add up to 140, that would have left angle R being 40, wouldn't it? Wanting to get 180 in every triangle. And these two triangles, 40 and 80, those two angles add up to 120. So what about angle Z? It's got to be 60 degrees, doesn't it? So I'm thinking, yeah, they both have a 60, they both have an 80, they both have a 40. So they are similar triangles. I'm going to name them in the proper corresponding order. Angle P, the 60, matches with angle Z. Angle Q, which was 80 degrees, matches with angle Y, also 80 degrees, and therefore it must have been ZYX. Now they're going to tell me some measures here, and we're going to try to write a proportion. If PQ is 4, I'll put that on my sketch. And PR is 8. Well, ZY, that length is 10. I guess that was this bigger triangle. Well, what can I know? What kind of ratio can I find and work out with XZ? Nice that I'm looking at this sketch. Opposite the angle with a measure of 40, I get this length 4. And opposite the same size angle here, I get a length of 10. So these are in a ratio of 4 to 10. Yeah, we ought to call that 2 to 5, huh? And I can use that to figure out any other length I care about. 2 is to 5 as, and that's the smaller one to the bigger one, since that was 10 and this is 4. And he wants me to figure out about XZ. XZ, opposite 80 degree angle, is going to go with that side RP, which is of length 8. As 8 is to what I'm looking for, and that's XZ. And we can solve that pretty quick, and I'm thinking that XZ would have been 40 divided by 2, therefore 20. So angles are a good thing to consider. And that will guarantee that triangles are similar, and when triangles are similar, we can write proportions and find their lengths. But there are a couple other methods. And the second way to know that triangles are similar is called side angle side. What must this mean? And it's not altogether obvious. Yes, it does say side angle side, but there's some things I'm going to write right here. So side angle side, I would say one pair of congruent angles and the surrounding sides in proportion. That's what side angle side means when we try to use it to find triangles that are similar. One pair of congruent angles and the surrounding sides in proportion. And we'll need an example or two. Looking at this one, tells me that AC is 8. Let's put this data into place, and BC is 12. CE is 18. That's this one. And CD is 12. Here we have a congruent angle, a pair of congruent angles, that is. Certainly those vertical angles are congruent, and I want to compare these other sides and see if, in fact, I have one pair of congruent angles and the surrounding sides, are they in proportion? And that's a smooth and thoughtful way to do that would be write in the proportion. And I'll take the shorter of these two sides in the smaller triangle, that would have been 8. And oughtn't I compare that with the shorter of the two sides in this other triangle? That would have been 12. Go back to the smaller triangle and give me the longer of those two sides. That would have been 12. And compare that to the longer of the two sides in the second triangle, which would have been 18. And we're wondering, are these sides in proportion? Are these surrounding sides in proportion? And a couple ways you can see that that's true. 12 times 12 is 144, and so is 8 times 18. So I'm thinking, yeah, these are in proportion. Also, both of these are in a ratio of 2 to 3. So yes, by golly, these triangles are similar. Let's make a similarity statement. I want to get this right. I know that Opposite that side of length 8 is angle B, and opposite the smaller side 12 is angle E. Angle B is going to match with angle E. Therefore, angle CA would have matched with angle D. I'm going to start with a D right there. And B, I reason, matches with angle E. My thoughts are there. The shorter of these two sides gives opposite that short side gives me this angle B, and opposite the shorter side here gives me that angle E. Those are corresponding parts. So this one must have been DEC. And the ratio between the two triangles is this ratio 8 to 12 or 12 to 18. Both of those are a ratio of 2 to 3. If AB is 10, okay, let's let this length be 10. Get the length of DE. Well, I have built the ratio. Let's put it to work. 2 is to 3. And that length 10 on the smaller triangle has to go in the numerator of this ratio in this proportion. And then I can find the length of DE. And I think you'd agree with me right away. Show that proportion, then you can give me the answer. DE is going to be 30 divided by 2, therefore 15. This length had to be 15. Let's play some more. I think we'll still be talking about side, angle, side for a minute longer. You've worked questions like this one before. Show that these triangles are similar by side, angle, side. I got to put in this data first. AE is 18. AB is 15. AED is 6. And BC is 5. I want to compare the lengths of the sides. As I compare these two triangles, I'm thinking about the side, angle, side relationship. They both have angle A. Let's consider the lengths around them. And I guess I want to figure out what is that full length there. That's got to be 24, doesn't it? I don't really want to compare sides of a triangle to sides of this trapezoid down here. Let's figure out that other length there as well. That one would have been 20. So, as I work to get these triangles to be similar, I'm going to take the shorter of the two sides on the smaller triangle. That's 15. We compare the shorter of the two sides on the bigger triangle, and that's got to be 20. Go back to this smaller triangle, give me the larger of those two sides. That had to be 18, as that would compare to the larger of the two sides here, 24. And both of these I recognize to be the ratio of 3 to 4. So, yeah, these triangles are similar in the ratio of 3 to 4. I ought to name them. And actually, when these triangles are similar, I know that this angle at E will be congruent to this angle at D. I know that these are parallel lines, and those are corresponding angles. So the angle at A will match the other angle at A. They are by the reflexive property. And the angle at E matches the angle at D. So this must have been ADC. And that gives me a length here. If EB is 10, find this length DC. We've done a couple problems like this before. I would say a good way to go would be 18. Comparing two sides of this smaller triangle is to 10. Then we compare two sides of the bigger triangle as 24 is to DC. So that'd be 240 divided by 18. I think I got that figured out. What's DC going to be? 240 divided by 18. Is that going to be 15, I think? Alexa, what's 240 divided by 18?
240 divided by 18 is approximately 13.3333.
Oh, I've got a problem here. 240. Alexa, 240 divided by 18?
240 divided by 18 is approximately 13.3333.
Oh, that makes sense, doesn't it? 40 over 6 goes into that one 40 times, 6 goes into that one 3 times. Yeah, that's got to be 13 1/3. My error. DC would have been 13 1/3. Happy to get that correction. Look at this one. It says it's a little bit trickier. It tells me that PD is 8 and TS is 7. PR is 10 and RQ is 2. And it's clear to me that these are not parallel sides. We're not having the same circumstance as before. But this small triangle and the big triangle might just be similar anyway. They both share angle P. And let me get that full length of this side for a moment. That would have been 8 and 7 would have been 15. And the full length of this side, 10 and 2 would have been 12. And let's compare some sides. See if we can get a ratio here. The shorter side of the smaller triangle, 8, is to the shorter side of the bigger triangle, that'd have to be 12, huh? As the longer side of the smaller triangle, 10, is to the longer side of the bigger triangle, 15. And we got to ask ourselves, is this a valid proportion? And in fact it is. They're both in a ratio of 2 to 3. Cross multiplication is still going to be 120 either way. So I'd say yes, these are similar. These sides are in proportion. Not the obvious one. In fact, I believe that the angle at T is going to match the angle at Q. These are not congruent. These are not parallel lines. But they were going to go. Get the ratio, and I think the ratio is 2 to 3. If I had made a similarity statement, it would have had to go like this. If I said TPR, triangle TPR is similar to triangle, and the angle at T matches the angle at Q. QPS. And it tells me if TR is 6, find this length down here. And it is true that TR and SQ, TR first and third, and SQ first and third, those are corresponding parts. And the ratio between these two triangles is 2 to 3. So 2 is to 3 as smaller triangle TR had length 6, excuse me. Therefore, I can figure out SQ. You'll have to agree with me that SQ is equal to 18 divided by 2, therefore 9. Okay, that's a little look at side angle side. A third way to know that triangles are similar, and this could happen every once in a while, side, side, side. And what would that have to mean to us? Side, side, side. To know that triangles are similar, all three pairs of sides are in proportion. If we know that this is true, then we would know that these triangles would be similar. And here I got a couple triangles that perhaps are similar by side, side, side. But we've got to figure out who goes with whom. And I would say, we're going to judge this by its appearance, and I think the angle at Q matches this angle at B. So I think that this side of length 4 is going to go with this side of length 4 square roots of 3. I'll begin with that. 4 is to 4 root 3 as, and let's say go to the hypotenuse. Let me just turn that off. Sorry about that. And then the hypotenuse of the smaller one, 8, compares with the hypotenuse of the larger one, 8 square roots of 3. As angle P is going to match with angle A, so I think these sides go together. As 4 square roots of 3 is equal to 12. And first thing we got to consider, is this a valid proportion? And since there are 3 parts, there's a couple things we got to check. Let me just cover up the last element. And if we cross multiplied here, if you multiplied 8 times 4 root 3, that would be 32 square roots of 3. If you multiplied 4 times 8 root 3, that would also give you 32 square roots of 3. So that's a valid proportion. Let me cover up the first element and do a little cross products here. And if I multiplied in this direction, 8 times 12 is 96. But if you multiply in this direction, just remember how you do that. The outside guy with the outside guy would be 8 times 4 would be 32. And the inside guy with the inside guy, the square root of 3 times the square root of 3 is going to be the square root of 9. So this is really just 32 times the square root of 9 is just 3. So that gives me 96. And we multiply this where we got 96 to go to that where we got 96. So this is also a valid proportion. So if that's a valid proportion, and that's a valid proportion, that's that is a consistent comparison between these numbers. These ratios are all equal. So these similar triangles, these are in fact similar triangles. Let's see what we can do about that. And I figure it's going to be in that same order. The angle at A matches the angle at P. But I think this may be useful. And the angle at B matches the angle at Q. and C matches the angle at R. Give the ratio between these two triangles. Let's do the shortest side to the shortest side. Shortest side of this one, 4. The shortest side out of this one, 4 square roots of 3. I wonder, can I reduce that ratio? And yes, I can. 4 goes into both of them. It becomes a ratio of 1 to the square root of 3. And then we're just going to use that to find a length. Almost got it all figured out. Stay with me, everybody. If the median from A to the midpoint of BC, let me just draw that from A to the midpoint of BC. I guess I could use a ruler. There's a median. Has the length 10. This length is 10. What segment could you know the length of in triangle PQR? And then we're going to find that length. And I would say, well, this angle A corresponds with this angle P, so the median from A to the midpoint of CB would correspond to the median from P to the midpoint of RQ. I'll show that. And I'm going to find its length. Might be kind of clever. I'll call it X for right now. We'll set up a proportion. I understand that these triangles, small one to big one, are in a ratio of 1 to the square root of 3. As the length of this median X is to the length of this median 10. And we're going to get kind of an ugly number out of this, but let's just see how that goes when I cross multiply. 1 times 10 is just going to be 10. Equals the square root of 3 times X. But I want to know about X itself. I got to get rid of this multiplication times the square root of 3. So I should divide this side by the square root of 3. And that necessitates that I divide the other side by the square root of 3. Happily, these are canceling. So I'm just left with X. And for the moment, we have X is equal to 10 divided by the square root of 3. And while that does have the proper value, it has terrible form. You're never supposed to leave a radical in the denominator of a fraction. I can't leave that square root of 3 in the bottom of that fraction. But I do like the value. I don't want to change the value. I just want to change the form. I'm going to multiply by the number 1. We're going to do this a lot in the semester ahead. I'm going to multiply by the number 1. What about the square root of 3 over the square root of 3? You might have to agree with me that that's equal to 1. And when I multiply this times 1, I won't change this value. But I'll get a value that looks a lot better. As I multiply straight across the top, as you would, it would be 10 times the square root of 3. And as you multiply straight across the bottom, the square root of 3 times the square root of 3 is the square root of 9, which is just a 3. So lo and behold, that is the answer right there. That would be the length of that segment, the median from P to midpoint of RQ. That median, let me just write that with you, would have been equal to 10 square roots of 3 over 3. And that's a kind of a fraction that we're going to get used to working with. Okay, I'll talk to you some more in a minute.